Good afternoon, I am Shelly Singla from GPC Kundi Majra. Today my topic is magnetic field, its units, field intensity, lines of force, their properties, magnetic permeability, susceptibility and their applications. So first of all, we will start with the topic of magnetic field. So magnetic field is defined as the space around a current carrying conductor or moving charge or a ferromagnetic material or a magnet in which its effect can be felt by another current carrying conductor or a magnet. Let us take a current carrying conductor. This is a conductor carrying a current I. Suppose we have kept a charge Q which is moving with velocity v in the near to this current carrying conductor, or suppose we have a magnet which is having two poles north and south, and we have kept another magnet having poles. So there is some space around this magnet or a current carrying conductor in which its effect can be felt by another magnet or a current carrying conductor or a moving charge is called magnetic field. Now next we come to the, let us take an example. Suppose we have a magnetic field set up by two poles of a magnet. As we know, there are two poles, north and south pole of a magnet, and a magnetic field is set up between these two poles. This field is B vector. Suppose we have a charge Q and it is moving with velocity, perpendicular velocity to this magnetic field. So a force will act perpendicular to both magnetic field as well as this velocity in the upward direction. This force is called magnetic force or Lorentz force. Magnetic force or Lorentz force Fm. This may be defined as, this is equal to charge itself Q into dot product, cross product of velocity vector into magnetic field vector. We can write it as Q V V sin theta into n cap, where n cap is a unit vector perpendicular to both velocity and magnetic field. So n cap gives us the direction of magnetic force. So let us take charge is equal to Q is equal to 1 coulomb, the velocity is equal to 1 meter. per second. So, and theta is equal to 90 degree. In that case, the magnitude of magnetic force Fm will be equal to magnetic field itself. So, we can say that magnetic field is equal to magnetic force whenever a charge of 1 coulomb is moving with a velocity 1 meter per second perpendicular to the given magnetic field. So, this is the definition of magnetic field. Now, next we come to the units of magnetic field. There are two units of magnetic field. First is SI unit. SI unit is Tesla, and we can define 1 Tesla is equal to 1 Weber per meter square, where Weber is the unit of magnetic flux. And CGS unit of magnetic field is 1 Gauss, which is equal to 1 Maxwell per centimeter square. This is in CGS unit. So, if we relate Tesla with Gauss, so 1 Tesla will be equal to 10 raised to power 4 Gauss. Now, from the expression of magnetic field, we have B is equal to Fm upon QV sin theta. So, taking the units of force as Newton, charge unit is coulomb, the unit of velocity is 1 meter per second, and if the value of sin theta is also 1, as theta is equal to 90 degree. So, the magnetic field will be equal to 1 Tesla, and this will be equal to 1 Newton per coulomb per meter into second. Newton second per coulomb into per meter, or we can write it as 1 Newton per ampere per meter. So, we can relate Tesla with Newton ampere meter. So, now the next is magnetic intensity. This is also known as intensity of magnetization. Intensity of magnetic field now, let us suppose we have two poles of a magnet. This is first pole and this is second pole M naught, and there is a separation R between these two poles. So, we can say that the intensity of magnetic field at a given point is defined as the magnetic force per unit north pole, per unit north pole. This can be related with the definition of electric field also. So, magnetic intensity is denoted by B vector. This is equal to magnetic force per unit magnetic north pole. This will be equal to mu naught mu r into m upon 4 pi into r square. So, this is the definition of into r cap, we can say. So, this is the definition of magnetic intensity in terms of magnet and distance r, and mu naught is the called magnetic permeability. Of vacuum, its value is equal to 4 pi into 10 raised to power minus 7. Mu r is called magnetic permeability. Relative magnetic permeability. So, next is magnetic lines of force. Magnetic lines of force are defined as it is a curved or straight line along which a unit north pole will move under the effect of magnetic force magnetic force. Let us take unit we can say unit north pole. If we draw magnetic lines of force for the north pole, they are radially outward. Like this. So, this is a line which can be straight line or a curved line along which this unit north pole will move under the effect of magnetic force. If we talk about south pole, the magnetic lines of force will be radially inward. So, unit south pole will have magnetic lines of force like this, and if we have a dipole magnetic poles north to south, then magnetic lines of force originate from the north pole and end at south pole outside the magnet, and from south to north will move inside the magnet. So, this is the direction of magnetic lines of force for a north south pole or a magnet. Now we can say that it is a line so that tangent drawn at every point of of it gives us the direction of magnetic field. We can draw the diagram. This is a magnet having north and south poles. So these are the magnetic lines of force from north to south pole outside, and from south to north pole inside the magnet. So we can say that if we draw a tangent at any point of it, let us take this point and we draw a tangent. This gives us the direction of magnetic field. So if we talk about this point, at this point this is the direction of magnetic field. So at various points of magnetic lines of force, we have various directions of magnetic fields. So now next is properties of magnetic lines of force. So there are some properties of magnetic lines. The first one is the magnetic line of force form the closed loops. As we have discussed now, that they originate from north to south pole, move outside, and from south to north pole inside the magnet. So they form the closed loop, unlike the electric lines. Electric lines do not form the closed loops. The second is the tangent drawn at each point of magnetic line gives us the direction of magnetic field at that point. This is the second property. The third is two magnetic lines of force never cross each other. Suppose we have a magnetic line and we have suppose we have two magnetic lines crossing each other. So at the point of intersection there will be two different directions of the magnetic field, which is not possible. So two magnetic lines of force never cross each other. Now the next property is magnetic lines do not exist inside a superconductor. Since a superconductor has zero resistance, so there is no magnetic line of force inside the superconductor. Then next is magnetic lines of force can pass through iron more easily than vacuum or air. Since the magnetic permeability for the iron is more as compared to vacuum or air, so magnetic lines of force can pass easily through iron. So now these are the some properties of magnetic lines of force. Next is magnetic flux. So let us draw a diagram. Suppose we have a given area. This is area. It is having surface area A. Now area vector is perpendicular to this surface area. It is denoted by A vector. Now let us take a magnetic field. This is line of magnetic field. The angle between magnetic field and area vector is theta. So this magnetic flux, this is denoted by phi m. It is a scalar quantity. This is defined as the dot product of magnetic field and area vector itself, or it can be also written as B into A into cos theta. Let us draw another diagram. Suppose we have a closed sphere and its total area is S, and we have small segment of surface area ds, and its area vector is ds vector. It is also kept inside a magnetic field B vector. The angle between B vector and ds is theta. So the small magnetic flux passing through this small surface area ds is equal to d phi m is equal to B vector dot ds vector. If we integrate it over the whole closed surface, we have total magnetic flux phi m. So this is its value will come out to be equal to 0. So we can define magnetic flux is equal to dot product of B vector, magnetic field vector and area vector. This can be also defined as the total number of magnetic lines of force passing through a given surface area held perpendicular to the direction of magnetic field is called magnetic flux. So, magnetic flux phi m is equal to V vector dot A vector. This is equal to B A cos theta. So, if the value of theta is equal to 0 degree, means B vector is parallel to A vector, magnetic field is parallel to area vector, then the flux will be equal to B into A. Cos 0 degree is 1. So, this is equal to B into A. This will be the maximum value of magnetic flux. If theta is equal to 90 degree, B vector is perpendicular to A vector and magnetic flux will be equal to 0. So, these are two cases of magnetic flux. Now, next is we come to the units of magnetic flux. We have in CGS, in SI system, the units of magnetic flux is 1 Weber. Since we know that 1 Tesla is equal to 1 Weber per meter square, so 1 Weber is equal to 1 Tesla into meter square. Tesla is the SI unit of magnetic field, and in CGS system we have unit of 1 Maxwell. 1 Maxwell is equal to 1 Gauss. 1 Maxwell is equal to 1 Gauss into centimeter square. So, if we correlate Weber with Maxwell, we can say 1 Tesla is equal to 10 raised to power 4 Gauss. 1 meter square is equal to 10 raised to power 4 centimeter square. So, this is equal to 10 raised to power 8 Gauss centimeter square. So, we can say that 1 Weber is equal to 10 raised to power 8 Maxwell. So, this is the relation between two units. Now, the next is electromagnetic induction. Firstly, we will draw a diagram. Let us take a coil and it is connected to a galvanometer. This is a galvanometer, and we have a magnet having north and south poles. Suppose we are moving this magnet near to this coil. Whenever we take this magnet near to the coil, then the magnetic flux will be more. There will be more number of magnetic lines passing through this coil, and if we take it away from the coil, the magnetic flux will be less. So, we are continuously moving this magnet near and far away from the coil. So, there is continuously magnetic flux changing. So, whenever the magnetic flux is changing, then galvanometer shows some deflection, means it shows some current. So induced EMF and induced current is produced whenever